Alright, the next thing we need to do is to delete from the heap. Once you're removing from a heap, you would delete the node that's at the root. So normally we then just copy this out into some variable, right, and use it. That's why heaps are very good at representing priority queues, because you can always find the smallest item very quickly and then reorganize the heap. Now to reorganize the heap to make sure that the partial order property remains in force, what you need to do is get rid of the last inserted position by copying the value that's in the last inserted position up to the root and then fixing. By comparing the root with the children and then replacing the root, whatever value is there, with the smaller of the children, if any smaller. So to delete one, you copy that out, maybe some box. Then you copy this value to the root. So we end up with 30, and 5, then 2, then 20, then 15. Of course, that doesn't follow the partial ordering property. We still need to do a swap here to fix a heap. So we do a swap. Giving us a 2 being the smallest thing that's remaining in the heap, or 5, or 30, and or 20, and or 15. Alright, the rest of this tutorial looks at analyzing an algorithm to actually reorganize a heap and ways of embedding heaps in arrays. I'm not going to spend too much time on that right now. We did discuss it in our sessions. What I'd rather spend time on is the tree rotations and how we insert into self-balancing trees. Because we need to finish that part today. So we'll be moving on to tutorial 5 after this. That's why one good point to take away from this is that we can use heaps to implement priority queues. We could have used a list to represent a priority queue. Of course, we're using a list to represent a priority queue. Then if we have n items in the priority queue, then the amount of time we take to insert an item would be, well, of course, it would depend on the process we use to insert it. With the list, you simply would have the option of checking the front item, checking each subsequent item to search for where to insert it, and that would be a theta process. So insertion into the list would be into the list that would represent the priority queue theta n. Deletion would be constant time, because you just take off the front item and then the rest would just be there. With a heap, you would have a time complexity of insertion that's proportional to the height, which is log to the base 2 of n. So we would end up, if we had to choose between a heap and a list to represent our priority queue, we look at insertion and deletion times of log n versus an insertion time of n to a constant time deletion. However, remember that once we're looking at the order of growth of the whole of the behavior of the application, you have to consider the whole set of operations. And if you want the full time, you need to sum all the operations. So the total time that we take to do a set operation will be the times to insert plus the times to delete. For the heap, we'd have log n plus log n. For the list, we have theta n plus theta 1, which is theta n. Okay, let me write it down. Here we're moving to a slightly higher level. Now, let's say we had to make a business decision to choose one implementation of an ADT, an abstract data type, versus another. So to represent priority queue using heap, let me say the time to insert is T insert. And T to delete equal theta 1. And theta n because we need to find the insertion position by checking each position along that set of items in the list. To represent a priority queue using heap, using binary heap, of course, once you sum all the activities, if you're going to be doing a set of inserts and a set of deletes, you're going to have theta n plus theta 1, which is a theta, which ends up as theta n. Over down here, you'll have theta log n plus theta log n, which is theta log n. So the time complexity of putting all those operations together will be better if we represent our priority queue using the binary heap. Now, you may also need to represent other types of repositories. A repository may be something, just something used to store data. Let's say you want to implement a database. And in a database, you may need to be able to put things in, take things out, and check if something is there. Now, your list you can check if something is in a list, but you can do a search. A heap is actually not a very good structure for searching, because it maintains a partial order property. You start here, and in order to check if a value is inside, you'd end up having to search. Now, your list you can check if something is in a list, but you can do a search. A heap is actually not a very good structure for searching, because it maintains a partial order property. You start here, and in order to check if a value is inside, you'd end up having to search both sides. The heap is actually not a very good structure that would be used for searching. A binary search tree, on the other hand, would be. Now, the binary search tree, we know, can give very good time complexity if it's balanced. But how we insert things into it determines the shape of the tree, which is not good. The heap is self-balancing, but it's not good for searching. So, what people who have been working on computer science procedures in the early days of computing have come up with is they've come up with a set of self-balancing trees. And these trees balance themselves using a rotation procedure. Hush. No, a tree is not balanced if the height of the left subtree differs from the height of the right subtree by more than 1. Now, if the difference between the height of the left and right subtrees is greater than 1, then tree is unbalanced. And we can fix that by rotating. One of the things we have to bear in mind is what we do in rotating. We know we need to rotate. As I said, because we have that height difference, and so therefore we're going to have at least 3 nodes in a tree that will need to be rotated. I'm going to label those nodes S, M, and L for small, medium, and large. Let's say we have our tree looking like this. And for this node, that would be the right sub tree. That would be the height of the right sub tree would be 2. Height of the left sub tree would be 0. Difference is greater than 1. So that needs to be rotated if we're going to make it balanced. So if we're going to rotate that to make it balanced, what would you do?
I would put the medium on the left.
Which one the tree?
There?
Which of the tree?
That one.
This tree, it's a binary. It's a binary tree and needs to be balanced. Let's say we have a binary search tree.
Oh, you can put the medium at the top.
So if the medium is in the root, small over to the left, and large over to right. So that way, we now have our tree having our left subtree being equal to the right height of the right subtree. What the balancing process does is reduce the height of one subtree by 1 and add 1 to the other. So it evens out the playing field. Alright, it's there. If another easy thing to recognize, easy configuration to recognize is if a tree looks like this with a large, medium, and small here. So it's easy to see that you're going to reorganize by rotating down. Medium, small over here, large over here. Interesting to note that regardless of the starting configuration, the ending configuration is the same. Now there are 2 other configurations that you need to worry about. You could have something like say small here, sorry, yeah, large could be over here, and medium here. Now, if you're writing a program to do that, you need at least 2 steps. You'd have to rotate the large around and then take the smaller off and put it over here. But the important thing for you to note is that the ending configuration will always be medium, small, large. Because that's the aim. You get this unbalanced tree, you want a balanced tree. The unbalanced tree will always have 3 nodes involved there, and then the balanced tree will take those 3 nodes and make them look like that. And the other configuration you could have is with large as the root, small attached to it, and then medium, which is greater than small here. Same ending configuration. Right, I'm not worrying about the intermediate steps with the double rotation, because this is considered double rotation here, with this going here and that going here. Interesting if you're writing a program, but to actually answer the problems to actually represent a tree being populated and the rotations being performed, I personally am not interested in that. So, one way of getting this to market, as they say, is to actually have a binary search tree and then have a function that will do the rotation if the things fall out of whack. Another way is to build these functions into an ADT. There's one ADT that was built called the AVL tree that actually kept a track of the heights of the left and right subtrees and then just triggered off a rotation if nothing, if something was unbalanced. Of course, in a project, then you're asked to implement that. Now, another tree that you'll meet is a red-black tree. If you remember from a red-black tree, it's basically a binary search tree with some additional properties.